Alright, 3, 2, 1. Alright, welcome to another online video. Hopefully the last one, but we'll see. So, as promised, we'll keep talking invertible matrices, connect them back to linear transforms, and set the stage for linear isomorphisms, which we'll talk about on Monday. Alright, and special guest with me today, we have Charlotte. Who's going to read the opening line and then leave me alone so I can record the rest of this video. Alright, so take it away, Charlie.
Yeah.
You said it right. Recall.
Recall that AERN times N is
Invertible
if there exists a B E R N X times N such that AB equals I. Is that right?
Yep, good job. Okay, get out of here.
Bye now, everyone.
Okay. Alright, there we go. So as Charlie said, a matrix is invertible if there is a matrix B so that A times B is equal to the identity. So what we proved last time is that this is all we need to verify that your matrix is invertible. A times B equals I is equivalent to B times A is I, for the square case anyway. And of course that matrix B is unique, and we denote it by A inverse. So our goal is to establish some formulas associated with this unique object, A inverse, talk about a way of actually computing A inverse given A, and then we'll tie it back to linear transforms. Alright. So, like I said, let's first start off with some formulas. So, some classic ones involving invertible matrices. A inverse itself is invertible, and the inverse of the inverse is the original. Given two invertible matrices, then their product remains invertible, and their inverse is the product of the inverses, but in reverse order. And again, that shouldn't be too shocking, because again, matrix multiplication is not commutative, so we'll see that B inverse A inverse is the correct inverse. We're able to circumvent the tyranny of non-commutativity with A times B equaling the identity, but unfortunately we can't escape it here. Transposing does not ruin invertibility, and the inverse of a transpose is the transpose of the inverse. The x of the y is the y of the x, our favorite phrase in mathematics. And then scaling by a non-zero scalar gives us an invertible matrix, and its inverse is what you would want it to be. Alright, and these are all super quick, thanks to this fact right here. So, since A inverse times A is the identity, that means A has to be the inverse of A inverse. So A inverse is A. Similarly, A times B inverse A inverse, because matrix multiplication is associative. Good thing I spent an entire day proving that. This collapses down to the identity, this collapses down to the identity, and these products here, we can just treat them as normal, so without having to worry about parentheses management. But anyway, this reveals that this must be the inverse of A times B, as promised. Right, and note, the order there matters. A inverse, B inverse would not work because I do not know that A, B times A inverse is anything. Alright, similarly for the transpose, as we noted, a product of transposes is the transpose of the product in reverse order, and the transpose of the identity is the identity. Alright, and then for scaling a invertible matrix, here we see that if we do this product, the scalars can be pulled out. They will scale to 1. This matrix will product to the identity, and 1 times the identity is, of course, the identity. So this object right here must be the inverse of that object right there, as promised. Alright, neat. So suspiciously, note that summation was missing from this. The inverse of a sum is not necessarily the sum of the inverses. I wonder if that'll be like an exam problem or something. Alright, that being said, now that we've established some basic formulas, let's talk about actual formulas for matrices. So here is what is, without a doubt, probably one of the most famous equations in mathematics. So put this in your brain next to the quadratic equation, because it's about that important. So given a 2 by 2 matrix, A, B, C, D, then our matrix is invertible precisely when this magic number is non-zero, and the formula for the inverse is given as follows. We swap the diagonal, negate the off-diagonal, and scale by 1 over the magic number. Ooh. Maybe you have encountered this number before in your math life. I'm sure you have. Alright, but the magic number, AD minus BC, why is this the thing that works? Well, if we let B be this matrix, this DA negative B negative C matrix, well, that times A should give me the identity, but scaled by this magic number, and indeed, if you multiply it out, you'll see that, hey, that works. Right, so if this matrix was indeed the inverse, then multiplying by it and scaling it should give me a scalar multiple of the identity. So now we see that if this magic number is non-zero, then scaling it over gives me that A times that is the identity, and thus it must be its inverse. Conversely, suppose the magic number is equal to 0. Well, now we'll show that our matrix has to be not invertible. If the magic number is equal to 0, then we know A times B is equal to 0. Now, what does that mean? Well, if A was invertible, then I can multiply both sides by A inverse and then get B is 0. But if B is 0, that means DA, negative B, and negative C are all equal to 0, which forces A to equal 0. And that means the rank of A is 0, but that means A can't be invertible, because as we proved, invertibility means you must be full rank. So A can't be invertible. So if the magic number is non-zero, then we are invertible. We have a formula for the inverse. And if you are invertible, then the magic number must be non-zero, because if the magic number is 0, then our matrix is not invertible. Magic. Pretty cool. So, like I said, put this in your brain somewhere. This is a very important formula. Absolutely essential formula, in fact. And pretty cool formula. And furthermore, very cool formula. All right. Now, so there we see a formula for the 2x2 matrix. And then naturally we then ask, well, given an n by n, is there a formula for the inverse? Very infamously for me, personal math story, once again. When I was in 11th grade, I was taking a pre-calculus, and so this would have been 2003. The teacher taught us the 2x2 formula, and then somebody in the crowd asked, hey, what's the formula for a 3x3? And he stone cold said there was no formula, which I called bullshit on. I'm like, there's got to be a formula. And then I spent the rest of the day cooking up the formula, and eventually I got it. And I came and gave it to him and said, hey, got it, you big liar. To which he responded like, well, yeah, there's a formula. Look at it. And of course, the formula is this big, massive mess of a thing. He then followed it up with, like, do you even know what any of those numbers are? Right, so I had this horrible formula, and I didn't know anything, and he was like, yeah, you don't know what this is. But he's like, there is a formula for n by n and beyond, but you need to use a certain tool. And perhaps you will determine it later. But for now, we're going to give a general method of computing the inverse, which doesn't give us a formula, it gives us an algorithm. And it's from the quick observation that a matrix is invertible precisely if it's a product of elementary matrices. Now remember, we've already seen a condition for a square matrix to be a product of elementary matrices. That happens precisely when you're row equivalent to the identity, which happens precisely when you have full rank. And as we've proven, being invertible is equivalent to having full rank. So there we go. Every invertible matrix must be a product of elementary matrices. Now, how can we use this to prove that we have like an algorithm of computing the inverse? Well, given an invertible matrix, it's a product of elementary matrices. This means, and recall, invertible matrices must be invertible because there is a matrix that we can multiply to get to the identity. So if I multiply both sides by the inverses of these elementary matrices, I'll get this, which means that A inverse has to equal this. So A inverse is the product of the inverse elementary row operations So these are the row operations that turn the identity matrix into A, and these are the ones that turn A into the identity. So in order to compute the inverse, you just got to figure out the row operations that actually convert the matrix A into the identity matrix. And a way you can do this is set up a n by 2n augmented matrix, and then get it into echelon form. So you row reduce and turn this into the identity. The row operations that turn this into the identity are precisely the row operations that yield A inverse, and they will be applied here. And there you go. So, you set up the n by 2n augmented matrix, you perform your row operations, identity matrix happens on the left, and on the right you get the inverse of A. So, that is the algorithm for generating the inverse of an n by n matrix. Now, note it doesn't give you a formula because the row operations you perform are going to be different depending on whatever the hell matrix you're dealing with. But this does give us a method of producing the inverse without necessarily having to have like a formula or anything. Alright, so for an example, if we had -4, 7, 6, 3, -5, -4, -2, 4, and 3 as our 3 by 3 matrix, we slapped the identity matrix on the right. I refed it, and by I refed it, I mean I asked a computer to give me the ref, and it gets us the identity matrix on the left, and on the right must be A inverse. And it's worth noting that this method will also detect if a matrix is not invertible, because if you set this up and perform the ref, over here we get not the identity matrix, which we know means that a matrix can't be invertible, and whatever we get over here is just some junk. But you can always ask a computer to just ref something for you, so you can always perform this, and this in particular reveals that this matrix is not invertible. Which we already knew this matrix wasn't invertible, because we know those vectors, the columns of those matrix fail to be linearly independent. Which we note is one of the many necessary and sufficient conditions for a matrix to be invertible. Alright, now that we've established some formulas for A inverse, and we have a general method of actually computing A inverse, let's see the connection between these things and linear transformations. So we went down this rabbit hole of invertible matrices because we saw something about invertible linear transforms. But before we can properly deal with that, let's prove a couple of things. So first of all, recall given functions f and g, their composition is the function g circ f, where you apply g to f. And it turns out the composition of linear mappings remains linear. Alright, and this is straightforward to prove. You want to show a mapping is linear, pick two scalars, pick two elements, feed in the linear combo. So what does s circ t do? Well, it applies s to t to the input. T is linear, so it pulls apart the input accordingly. And S is linear, so it pulls everything apart accordingly as well. And there we see that S circ t of alpha x plus beta y is alpha S circ t of x plus beta S circ t of y. So the composition of S and t is in fact a linear mapping as promised. Alright. And now let's note that, hey, linear transforms in Euclidean spaces have matrices associated with them. So it'd be really nice if the composition of those linear mappings, the matrix for it was like, matrix multiplication. Oh, and it is. Look at that. Indeed. So if you have a matrix T and a matrix, a linear transform T and a linear transform S that have matrices A and B as their standard matrices, then the product is the standard matrix for the composition. Right, and note here I'm keeping track of all of the dimensions accordingly and carefully. Alright, and in order to prove this, we know the standard matrix is unique, so we just need to prove that feeding x into T of S, T circ S, just gives us A times B times x. Alright, so S circ T, feed in x, you get T of S of x. S has B as its standard matrix, so this is B times x. T has A as a standard matrix, so we have A times that, and hey, good thing I spent an entire day proving that matrix multiplication is associative, so I can move those parentheses over, verifying that T circ S's matrix is indeed A times B. All right, and then now we make the connection of invertible matrices and invertible linear transforms. Indeed, if we have a linear mapping generated by a matrix, A is invertible precisely if T is formally invertible, and its formal inverse is given by the inverse of the matrix. Ah, beautiful. There we go. So, linear transforms being formally invertible, linked directly to matrix multiplications invertible elements. Hooray! We did it. Alright, so let's actually prove this. So, if A is invertible, then we have access to a linear transform generated by A inverse. The standard matrix for S circ T and T circ S is A inverse times A and A times A inverse, both of which are the identity matrix. So S of T of X must be the identity matrix times X, which is X, and likewise T of S of X is the identity matrix times X. So S must be the formal inverse of T, because composition on either side gets us the identity. Conversely, suppose that T is a formally invertible mapping. T inverse, as we proved, must be linear, and so we have a matrix B that represents it. But as we just proved, T circ T inverse must have A times B as its standard matrix, but what is T circ T inverse of X equal to? Well, it's the identity times X, which means that A times B must be the identity, and thus A is an invertible matrix, as promised. There we go. So we've connected matrix multiplication to composition of linear transforms, and the formal invertibility of such transforms coincides with the matrix multiplication's invertible elements. Very beautiful, very cool. Very cool. And there we go. All right. So, next time on Monday, what are we doing? We are going to dig deeper into the formally invertible linear transforms, which are in the general setting of vector spaces. Those are known as linear isomorphisms. Ooh. So, we will go a little further with that. All right. That's it for this video. I'll see you next time.